J.J. Thomson's experiments with the discharge tube with different gases filled in it, one at a time, led to the conclusion that all the elements contain negatively charged particles, which were later called electrons. Since the atom is electrically neutral, it was proposed that the atom must also contain positively charged particles in it, such that the total negative charge in the atom is equal to the positive charge in it. Based on these assumptions, J.J. Thomson proposed the plum pudding model of the atom. In this model, he proposed that the total positive charge in the atom is spread throughout its volume, and the negatively charged electrons are distributed in this volume like seeds in a watermelon. But subsequently, an experiment proposed by Ernst Rutherford and carried out by his students Hans Geiger and Ernst Marsden, to understand the structure of the atom, proved that the plum pudding model of the atom was not in agreement with the results of the experiment. Rutherford proposed that the scattering of the alpha particles from atoms of an element would be helpful in understanding the structure of the atom. Let us now study and understand the Rutherford's alpha particle scattering experiment, which led to Rutherford's nuclear model of the atom. The experimental setup consisted of a source of alpha particles, like bismuth-214, placed in a cavity in a lead block, and the arrangement was made to obtain a narrow beam of alpha particles by passing them through space between lead bricks. Here, we should remember that the alpha particles were actually helium nuclei. As we know, the charge of the alpha particle is 2 times the charge of the proton, and its mass is 4 units. The narrow beam of alpha particles so obtained was allowed to fall on thin gold foil of thickness around 2.1 into 10 to the power minus 7 meter, that is 0.21 micrometer. The scattered alpha particles were made incident on a zinc sulfide screen. The zinc sulfide screen being a fluorescent screen, the alpha particles upon striking the screen caused scintillations leading to the detection of their presence. The scintillations were observed through a microscope. This entire arrangement was enclosed in a vacuum chamber to avoid stray particles, if any, entering the experimental area. It was observed experimentally that most of the particles passed off straight through the gold foil without any deviation in their path. A few of them suffered minor deviations, and very few of them suffered large deviations. These deviated particles were studied as a function of the angle of scattering. Angle of scattering is defined as the angle between the path of incident particle on the gold foil and the path of the scattered particle away from the gold foil. A graph was plotted between the number of scattered particles detected on the y-axis and the scattering angle on the x-axis. Based on the data from the graph, Rutherford made the following conclusions. The number of particles for nearly zero angle of scattering was very large, indicating that most of them had passed almost straight through the gold foil. This implied that most of the atoms must have been empty. Out of all the incident alpha particles, only about 0.14% of the particles scattered by more than 1 degree. This was due to the fact that these particles passed close to the central part of the atom, which must have been positively charged. And 1 in 8,000, that is about 0.0125% of the incident alpha particles scattered by more than 90 degrees, that is, they scattered backwards. For this to have happened, such alpha particles must have experienced a large repulsive force. This would be possible only if most of the atom was empty and its entire positive charge was concentrated tightly at the central part called the nucleus. In such a case, the alpha particles which moved very close to the central part would experience large repulsive forces and suffer deflections greater than 90 degrees. Based on these assumptions, Rutherford proposed the atomic model, henceforth called the Rutherford's nuclear model of atom. The entire positive charge and most of the mass of the atom is concentrated at the center of the atom called the nucleus. He also proposed that the electrons revolved around the nucleus in orbits, just like planets revolving around the sun. Hence, the Rutherford's atomic model is also known as the planetary model of the atom. Based on Rutherford's experiments, the size of the nucleus was estimated to be around 10 to the power minus 15 meter to 10 to the power minus 14 meter. According to the kinetic theory of gases, we know that the size of atom is about 10 to the power minus 10 meter. So, the atom is about 10,000 to 100,000 times larger than its nucleus. Now, by using Rutherford's nuclear model of the atom, we can explain the scattering of alpha particles from the gold foil. As the gold foil is very thin, it can be assumed that the alpha particle undergoes one scattering due to the gold nucleus. So, to calculate the trajectory of an alpha particle, it is enough to consider the scattering of an alpha particle by a single gold nucleus. The atomic number of gold is 79. That is, the nucleus of gold contains 79 protons. Therefore, the charge on the gold nucleus is equal to 79e, where E is assumed to be the charge on each proton. Hence, the gold nucleus is approximately 50 times heavier than the alpha particle. Hence, it can be assumed that the gold nucleus remains stationary during the scattering process. Now, according to Coulomb's inverse square law of electrostatics, the magnitude of the repulsive force between the alpha particle and the gold nucleus F is equal to 1 by 4 pi epsilon naught into 2e into Ze by r square, where r is the distance between the alpha particle and the nucleus of the gold atom. This force acts along the line joining the alpha particle and the nucleus of the gold atom. The direction of this force and its magnitude continuously changes as the alpha particle approaches or recedes from the nucleus. The path of the alpha particle depends on the impact parameter b for the scattering, which is defined as the perpendicular distance between the direction of the initial velocity of the alpha particle and the nucleus of the gold atom. The alpha particles have a range of impact parameters. So the alpha particles are scattered in different directions. If the impact parameter is large, the alpha particles pass without deviation. That is, the scattering angle is approximately 0 degrees. For relatively small values of b, that is, when the alpha particles are directed very close to the nucleus, there are huge deviations. If the alpha particles are directed in the same line as of the gold nucleus, then they undergo a head-on collision, in which case the impact parameter is the least and hence the scattering angle is approximately 180 degrees. Therefore, such alpha particles bounce back. Since very few of the incident alpha particles undergo head-on collision, it can be said that the mass of the gold atom is concentrated in a very small region called the nucleus. According to the Rutherford model of the atom is electrically neutral. It was proposed by the Rutherford model of the atom that the centripetal force Fc on the revolving electrons was provided by the Coulomb force Fe of attraction between the electron and the nucleus to keep them in their orbits. Let us apply this concept to the case of a hydrogen atom. A hydrogen atom consists of one electron revolving around its nucleus, which is actually the proton. For the electron revolving with speed v, the centripetal force Fc is equal to mv square by r. The electrostatic force of attraction Fe between the electron and the proton in the nucleus of the hydrogen atom, separated by a distance r, is given by Fe is equal to 1 by 4 pi epsilon naught into E square by r square. This is true because the proton and the electron have equal magnitude of charge E on them. But for dynamically stable orbits, Fc is equal to the electrostatic force Fe. Hence, mv square by r is equal to 1 by 4 pi epsilon naught into E square by r square. Let this be equation 1. On simplifying equation 1, we get the radius r is equal to E square by 4 pi epsilon naught mv square. Let this be equation 2. From equation 1, we also have v square is equal to E square by 4 pi epsilon naught mr. Let this be equation 3. The kinetic energy of the electron in the hydrogen atom is K and is equal to half mv square. Substituting v square in the expression for kinetic energy, we get K is equal to E square by 8 pi epsilon naught r. Let this be equation 4. The electrostatic potential energy of the electron, U, is equal to minus E square by 4 pi epsilon naught r. Let this be equation 5. The total energy of E of the electron in the hydrogen atom is equal to the sum of the kinetic energy K and the potential energy of the electron U. By substituting the expressions for K and U and simplifying, we get E is equal to minus E square by 8 pi epsilon naught r. So, the total energy of the electron is negative. This implies that the electron is bounded to the nucleus. When a metallic body is heated, it emits electromagnetic radiation. The radiation may consist of different wavelengths. The electromagnetic radiation may consist of different components having different wavelengths. For example, when the filament of an electric bulb is heated, it emits white light consisting of radiations in the visible range. When this white light is passed through a prism, we obtain a continuous spectrum consisting of all the wavelengths in the spectrum. This spectrum appears as bright lines where one color gradually merges into the other, without a clear demarcation between the adjacent colors. Similarly, when hydrogen gas, which is enclosed in a sealed tube, is heated to high temperatures, it emits radiation. When this radiation is passed through a prism, we obtain the hydrogen spectrum. This spectrum is not a continuous spectrum. It consists of some sharply defined, discrete